Welcome, fellow aviators. Today, I'm going to be reviewing the operational principles of the propeller system for one of the most commonly used turboprop engines in the industry, the PT6. So, without further ado, let's get into it. There are many principles that must be understood to fully comprehend how the PT6 propeller system works. I will start with general principles that apply to all propeller systems, and then move into the specifics of the PT6 design as the depth increases. The first principle is arc velocity. As an airfoil spins, different parts of the blade follow different tracks. The further away from the hub you get, the longer the track the blade must follow, and the greater the speed of the blade. The entire blade remains at the same RPM, but the further you get from the hub, the higher the airspeed becomes. Because airspeed is a major component of the lift equation, arc velocity causes the lift produced by a rotating airfoil to increase as you move away from the hub. The resulting force can cause the airfoil to bend when thrust is produced. This force is negligible on most modern propellers due to the incorporation of blade twist. However, the longer the airfoil gets, the less effective blade twist becomes. PT6 engines equipped with large propellers will have lower RPM limitations to help mitigate this problem and maintain structural integrity. To minimize thrust bending and more effectively distribute thrust production, the angle of attack of the blade changes along the length of the blade. The slower the rotational speed of the blade, the higher the angle of attack. The angle of attack must be kept between 0 AOA and the critical AOA, approximately 16 degrees, to maintain lift production. Blade twist can effectively alleviate thrust bending on short airfoils, which is most propellers. However, when the airfoil becomes sufficiently long, compensating for thrust bending would require the interior of the airfoil to be stalled while the outboard portions are creating reverse thrust. Obviously, this is less than desirable. So, when airfoil length exceed blade twist capabilities, the airfoil must be designed to withstand the thrust bending forces it will experience. The PT6 engines equipped on helicopters will utilize these types of airfoils, and the resulting bending up of the rotor blades is referred to as coning. Every time an airfoil completes a rotation, it should move forward a certain distance based on the average pitch of the blade, like a screw moving through wood. This ideal distance is the geometric pitch of the airfoil. However, the aircraft is often not moving at the ideal speed for the design of the airfoil. In these cases, the distance that the airfoil actually moves forward in one rotation is referred to as the effective pitch. Any difference between the effective pitch and the geometric pitch is known as slippage. Propeller slip is wasted energy. Instead of producing thrust, it uses engine energy to tear up the air like a screw that is turned, but not allowed to move forward. Helicopters will never be able to obtain geometric pitch due to the effects of weight, but airplanes can. This allows airplanes to carry much more weight with smaller engines. However, geometric pitch can only be maintained at one speed. Thus, fixed-pitch propellers are identified by the speed that they are effective at. Climb props capture effective geometric pitch at low speeds, while cruise props capture it at faster speeds. Variable pitch or constant speed propellers can change pitch in flight to act as a climb prop at slow speeds and a cruise prop at faster speeds, thus maintaining effective geometric pitch over a wider speed range. Once the spinning airfoil is allowed to change pitch, several other factors become involved in determining propeller pitch. The first we will discuss is called aerodynamic twisting. Aerodynamic twisting is simply the impact that the wind vane effect has on the rotating propeller. As it spins around, all the wind impacting the blade forward of the pivot point will try to increase the blade pitch to coarse pitch, while all the wind aft will try to push the blade to a lower or finer pitch. There is more surface area aft of the pivot point, so the resulting aerodynamic twisting force will push the blade towards fine pitch in line with the plane of rotation. The faster the prop spins, the stronger the aerodynamic twisting effect will become. To counteract the aerodynamic twisting force experienced by the propeller, counterweights are placed on the blade near the hub. These weights are placed forward of the pivot point of the blade to ensure a forward CG. The exact position and weight of the counterweights is specific to the individual prop design. As the propeller begins to spin, the centrifugal force generated affects the blade on its center of gravity, which pulls the prop towards course pitch. The faster the propeller spins, the more centrifugal force is generated. When calibrated correctly, this centrifugal force twists the blade with the same amount of force in the opposite direction as aerodynamic twisting, effectively canceling each other out. This is why the weights counteracting aerodynamic twisting are called counterweights. Many pilots erroneously believe that these weights move the propeller towards the feathered position. They do not. While counterweights do produce force towards course pitch, they only produce sufficient force to counteract aerodynamic twisting, not move the blade. This is a cutaway that Hartzell has produced and is available for viewing in their factory. However, other manufacturers have very similar designs. The counterweight is attached to the blade hub and serves to counteract aerodynamic twisting. Some designs may incorporate counterweights that are contained inside of the blade to accomplish this same purpose. The propeller blade hub secures the propeller to the hub assembly. The propeller piston engages the blade hub through hub pins and creates rotational force when moved forward or aft. The propeller hub pins attach the propeller hub to the propeller piston to translate linear motion into rotational force. Multi-engine aircraft will move the blades towards course pitch as the propeller piston moves aft. Single-engine aircraft will utilize the empty slots shown here to produce a fine pitch movement of the blades as the propeller piston moves aft. This provides a failure mode of fine pitch due to the force provided by the hub spring. The hub spring pushes the propeller piston rearward. This spring can be aided or replaced by a nitrogen-charged pressure vessel on some designs. The forward and aft pitch stops, sometimes referred to as high and low pitch stops or fine and coarse pitch stops, provide a hard stop to prevent the propeller from moving beyond the design degree limitations. If the propeller is designed with beta ranges, it will have multiple beta rods to provide an adjustable fine pitch stop. The beta rods actuate the slip ring, sometimes called the feedback ring. The slip ring is located outside and aft of the prop hub and is used to actuate the engine-mounted components of the beta system on aircraft equipped with thrust reversing. Blade angle is measured between the resultant relative wind, which is primarily determined by the direction of travel, and the mean aerodynamic chord, or MAC, which is an average measurement of the line from the leading edge of the airfoil to the trailing edge. Propeller operation ranges are broken up into several categories that are used for different phases of flight. Single-engine aircraft typically do not allow movement to the full course or feather position, and aircraft without reversing capabilities typically do not allow movement into the beta range. Here we see the propeller in the 90-degree or feathered position, moving through the course pitch ranges, the flight fine position, the ground fine position, and movement into the reverse ranges. Beta range requires the pilot to move the power levers over the gate and should not be used in flight. The reverse beta range is controlled by the power lever being over the second gate from -2 to about -15 degrees. The forward beta range is still controlled by the power lever being over the first gate between 11 and -2 degrees. The alpha range, or flight fine, is controlled by the prop lever and consists of the range between 30 to 11 degrees. The alpha range in the course setting is controlled by the prop lever and comprises the ranges between 90 to 30 degrees. And the full course pitch in the alpha range is considered feathered. Now that the vocabulary is out of the way, let's take a look inside to see how this works. I have represented oil in the hub for ease of visualization. While oil pressure does control the prop piston movement, this interaction takes place in the engine to avoid the difficulties of trying to create an oil seal to a rotating component. If oil was pumped into the prop hub, seal failure would be a frequent occurrence and result in all the engine oil being pumped out through the prop and a subsequent engine failure. Needless to say, this situation is best avoided. As oil pressure moves the prop piston forward, we move through course pitch. Moving further forward gets us to flight fine, and as we reach the movable low pitch stops, we reach the ground fine setting. Movement into the beta and reverse ranges requires the stops to be adjusted. Now that we know how the propeller moves, let's take a look at what controls the oil pressure. The oil pressure that determines the pitch of the propeller is controlled by the primary governor, also called the constant speed unit, or CSU. The oil pressure is supplied from the engine sump by the engine-driven oil pump at approximately 80 psi. When it reaches the primary governor, the governor high-pressure pump increases the oil pressure to approximately 375 psi. If the oil pressure exceeds 400 psi, the pressure relief valve opens to vent excess oil pressure. When the pressure falls back down to the desired 375 psi, the pressure relief valve closes to maintain operating oil pressure for the primary governor. The first condition we will address is referred to as an overspeed condition. When the RPM exceeds the set value, the flyweights will be pulled outward by centrifugal force. This motion will lever the pilot valve upward. As the pilot valve is moved, oil pressure is vented from the prop hub back to the engine sump. This effectively reduces the amount of oil pressure at the hub. The result of reduced oil pressure at the prop hub is that the hub spring pushes the piston rearward and the blade angle becomes more coarse. The new blade angle increases the drag on the propeller and slows its rotation. Reduced RPM lowers the pilot valve back down to the on-speed condition. When an underspeed condition is encountered, the speeder spring force will exceed the force of the flyweights and the pilot valve will be lowered further. This allows high-pressure oil to the prop hub, which exceeds the prop hub spring force. The result is that the prop piston moves forward, the blade angle is reduced, and the prop RPM increases back up to the desired setting. The pilot controls the RPM by using the prop lever in the cockpit. If a lower RPM setting is selected, tension on the balance spring is reduced, and the worm drive is subsequently adjusted to reduce tension on the speeder spring. The lower tension on the speeder spring causes the centrifugal force of the flyweights to lever the pilot valve upward. This causes the pressure in the prop hub to be vented back to the engine sump. As the oil pressure drops, the prop moves to a coarser pitch. The increased drag slows the propeller to the desired RPM setting, and the system is now on speed at a lower RPM setting. If the pilot desires a higher RPM setting, the prop lever is moved forward, which increases tension on the speeder spring. The speeder spring pushes the pilot valve down, pressure flows into the prop hub, and the prop piston moves forward. This causes the propeller to pitch to a finer setting. The reduced drag of the finer angle of the propeller increases RPM, and the governor returns to an on-speed condition at the new higher RPM. We have covered how the governor works normally. However, if these systems fail, the result could be an uncontrolled increasing of RPM. This uncontrolled increase of RPM would lead to catastrophic system failure. Next, we will cover the systems that are designed to intercede and prevent that from happening. The overspeed governor is a separate unit that has two main functions. It provides electronic RPM control via the solenoid or dump valve and overspeed protection via the physical governor or overspeed governor. The physical governor is set to close at 104% of maximum RPM. When 104% is reached, the flyweights extend due to centrifugal force, and the pilot valve blocks the supply of oil to the primary governor. The pilot now has no control over the propeller setting. It is permanently set to 104% until repairs can be made. The solenoid valve has two functions. First, it allows the pilot to test the function of the overspeed governor. This is accomplished when the pilot pushes the prop test switch and the solenoid moves to the test position. This allows the pilot to test the function of the overspeed governor during a run-up without an actual failure. With the prop test switch activated, the overspeed governor will engage at 92% of maximum RPM instead of allowing the RPMs to climb all the way to 100%, where it will be governed by the primary governor. This vents oil from the reset spring and lowers the tension on the overspeed governor's speeder spring, effectively lowering the engagement point from 104% to 92%. The second function of the solenoid is to engage the auto feather system. When the auto feather system is engaged, the solenoid vents all the pressure out of the prop hub, and the prop spring moves the propeller to the feathered position, regardless of the primary governor position. Due to the wiring of the auto feather system, There are several steps that must be completed for the system to engage. First, the system must be armed by the pilot using a switch in the cockpit. The system is activated when a microswitch is closed by the power lever reaching approximately 90%. This also activates the annunciation light to the pilot. This switch can be bypassed by holding the auto feather switch in test for a pre-flight test of the system. If torque is reduced below 400 foot-pounds with the 90% switch or the test switch active, it deactivates the auto feather system for the opposite engine. This ensures that the auto feather system cannot feather both engines at the same time. If the torque continues to decrease below 200 foot-pounds on the activated engine, the solenoid switch, sometimes referred to as the dump valve, is activated, and the propeller moves to feather as prop hub pressure is vented. The last form of overspeed protection is the fuel topping governor. This is an inaccurate name, as the fuel topping governor is not a governor at all. Rather, the fuel topping governor is a fuel regulating overspeed protection feature added to the primary governor. The fuel topping governor is set to 106% of the RPM selected by the pilot. This is accomplished as the speeder spring cup engages the fuel topping governor reset lever. The fuel topping governor reset lever breaks the PY seal and allows PY air, sometimes referred to as bleed air or P3 air, from the fuel control unit to be vented out. Because PY air is used to regulate fuel flow, this causes the fuel flow to be reduced to the flight idle setting. This reduction of engine power occurs regardless of current propeller pitch or oil pressure when the fuel topping governor is engaged. The fuel topping governor remains set to 106% of the set RPM because the reset arm moves with the prop lever. The movement of the reset arm allows the reset spring to push down the reset lever and remains set to the speeder spring cup. If the primary governor fails, the fuel topping governor will also be unable to function, and RPM management will be solely managed by the overspeed governor. But if the primary governor is functional, it will continue to enforce a power reduction at 106% of the set RPM. The next feature of the PT6 prop governor is the ability to use reversing function. This is accomplished by the use of the beta system. The prop governor interacts with the beta system via the beta valve and beta lever. During normal operations, the purpose of the beta system is to prevent the prop from entering the beta range. This is typically encountered at low power settings, when low RPM will result in an underspeed condition in the constant speed unit. When oil pressure pushes the prop into the beta range, the beta lever engages the slip ring using a carbon block. As the system begins to move, the beta valve cuts off oil pressure to the governor and vents it back to the sump. This causes the system to return to alpha, and the beta valve acts as a governor in this range. During ground operations, when the pilot pulls the power levers over the second gate, three functions are accomplished. First, the beta lever is pivoted rearward due to the walking beam design. This allows the beta valve to move without adjusting the slip ring. From the rearward position, movement of the beta valve does not restrict oil flow, and pressure is now maintained at the prop hub in the beta range. The second function that is accomplished by going over the second gate with the power lever involves the fuel control unit. Over the second gate, the power lever is commanding the fuel control unit to increase power production to create sufficient reversing thrust for stopping. Prior to moving the power lever over the gates, it is critical that the prop lever be set to the full forward position. This maximizes speeder spring tension and will ensure that the constant speed unit stays in the underspeed condition. Failure to do so will cause the reverse not ready caution light when the landing gear is down. If reverse is selected by the pilot in this configuration, everything will appear to function as normal at first. The propeller will enter beta and begin producing reverse thrust as commanded. However, as the power increases, the propeller will accelerate until an overspeed is sensed by the constant speed unit, which will start venting pressure to correct the issue. The prop responds by moving from a negative angle of attack to a finer pitch. This increases propeller speed rather than decreasing it. The primary governor vents even more pressure, and the prop rapidly overshoots into positive thrust. The result is a massive amount of asymmetrical thrust that will likely leave the aircraft uncontrollable in a multi-engine and dramatically increase landing distance in a single-engine aircraft. The consequences of this situation are so great that there is more safety features built into the PT6 design to prevent this from happening. The third function accomplished by placing the power lever over the second gate is to lower the fuel topping governor setting to 95%. If the CSU moves towards an overspeed setting, the fuel topping governor will vent PY air and depower the engine before a transition to alpha range can occur. The last component of the PT6 propeller control system only applies to multi-engine applications. It is called the syncophaser, or commonly referred to as prop sync. The noise produced by multi-engine aircraft propellers can match resonant frequencies and create a wah-wah sound that is uncomfortable for passengers and can create vibration damage over time. To prevent resonant frequency harmonics, the syncophaser monitors propeller RPM via an electronic tachometer. The control box then compares the signals received from the tachometer and varies the signal strength to a coil mounted on the primary governor accordingly. These coils are capable of biasing the primary governor settings sufficiently to match RPM without pilot intervention. When propeller RPM has been harmonized, the control box will stop its inputs. If the required adjustment is beyond the capabilities of the syncophaser, or the system has failed, pilot intervention may be necessary to maintain prop harmonics. This can be accomplished by utilizing the prop sync indicator, or PSI. If the pilot notices the wah-wah sound and looks down to see the prop sync indicator spinning, simply adjust the props in the direction of spin. The slower the spinning, the smaller adjustment needed to harmonize the propellers. The prop sync indicator should stop spinning once harmonization is accomplished. However, no adjustment is needed once the props are harmonized if the prop sync indicator continues to rotate. The prop sync indicator only indicates direction of adjustment, not harmonization. And that is the fundamental operating principles of the PT6 constant speed propeller system. Thank you for watching. If you found this content to be helpful, please like and subscribe, and together we will use the jet fuel of passion to power our climb to quality. Stay safe, keep climbing, and I'll see you on the next one.